So where we just spent those last two videos talking about average rate of change across 2 points and the secant line that's created across 2 points, now we want to talk about when those 2 points get infinitely close to each other and how it creates this instantaneous rate of change. So this page has a lot of definitions and explanations, so we're just going to kind of talk through them and then play with these ideas a bit. So first off, average rate of change for f of x goes from two coordinates, x1 to x2, and it represents the slope of the secant line between those two coordinates. So for this graph up above here, if we graph this x squared, if we look for the average rate of change from x equals 1 to x equals 2, that average rate of change is equal to 3. So visually what we're seeing here is we have our parabola, so I have my two coordinates 1, 1 and my coordinate 2, 4. If I draw the line between those 2 points on that function, that line created, that's called our secant line. And with that, our average rate of change is equal to the slope of that line. And what we're seeing is that it has a slope of 3. So that's what we covered in those last two videos. So what we want to talk about here is as that interval shrinks. So right now we have this space, in this case it's a unit of 1, and as we shrink the space between those two coordinates, it becomes a tangent line. And the slope of that tangent line measures the rate of change of that function at that exact point, and that's what we called our instantaneous rate of change. So it's a rate of change at that exact point as we shrink down that distance between the 2 points. Right now what we're doing is we're just going to work visually in estimating this instantaneous rate of change, but a big basis of calculus and what we're going to be doing over the following weeks is figuring out how to find this algebraically as well as using calculus to find that slope of this tangent line. So what that means is if we focus in on our coordinate 1, let's focus on this point here. What we could do is imagine that I'm kind of traveling along the parabola, getting closer and closer. And if we keep visualizing that secant line, it's that secant line's getting closer and closer until we're infinitely close. And then you could even imagine like zooming in right at that point, and we're trying to match up the slope right at that coordinate. Something like this. Probably even a little bit steeper. Something like this. And honestly, because I've taken calculus before and I'm teaching it, I know what the slope should be. So this is kind of a new concept for you. And in the next examples, I'll show you how to kind of think about this too. But what we want to do is imagine a line that just touches at that coordinate. And in this case, it's going to be a line with a slope of 2 that goes through that point. Let's get something like that. And let's get that out there. Okay, sorry, took a little bit there. So this line that I drew right here, it's just touching at that coordinate 1, 1. It's not going through any other coordinates on the graph. And the idea is that we're matching that slope just at that point. So if we imagine a point infinitely close and found that secant line, it would be roughly matching up with this line here. So this line that we're graphing, that is called the tangent line. And what we would see with this tangent line in this case is it has a slope of 2. And then for these with tangent line, the slope is going to relate to instantaneous rate of change. So instantaneous rate of change is equal to the slope, which in this case is equal to 2, just from visually looking at the slope of that line there. So that's where we're headed with calculus, is looking at rate of change at a single point on our function. So just to go back to our definitions here, instantaneous rate of change is interchangeable with slope of the tangent line, which is interchangeable with derivative at a point. So these things all represent the same thing for us, and we'll use them interchangeably, but really the process will be the same if we need to calculate any three. And at this point, as we work with it, we could think of it as this f of x plus h minus f of x over h as h approaches 0. That notation right there, what it's doing is it relates to what we did in that last example that was kind of abstract here, is it says we have our value, but let's actually call it x, and then we would have an x plus h. And then what we want to do is figure out what happens as h shrinks down to 0 so that it's basically infinitely close to our x value. So what ends up happening with this, and this is called our difference quotient, and this is really at the base of how we calculate derivatives for everything in calculus. But the idea is that down here, it's still really our average rate of change. It was like we had x plus h minus x, but that's just going to simplify down to h there. So this sets up our average rate of change for something that's a little far from x, whatever distance h is, and then our original value for x. And then we want to see what happens as h approaches 0. Now, a big basis for what we do in calculus 2 is this idea of approaches, because if I just said evaluate this for h equals 0, it's immediately undefined. Plugging in 0 into that denominator breaks everything and nothing works. And then calculus doesn't exist, and we don't want that to happen. Instead, it's the idea of getting h infinitely small. So as it gets closer and closer to 0, what's happening to this rate of change? And that's where this instantaneous rate of change comes through. And then this last sentence just summarizes what I drew up at the top there. So we have our function x squared, and then just looking at the coordinate x equals 1, we have this instantaneous rate of change of 2 coming from the slope of that tangent line. Lots of terminology here, and we're just going to revisit it again and again. They're just these pieces that we're going to use interchangeably, that really the process will be the same with the setup of given a function, given a point that we want to evaluate, finding this instantaneous rate of change or slope of the tangent line or derivative at a point. So let's start putting some of this into practice with examples here. So we have a rock is shot upward with a velocity of 80 meters per second. The height after t seconds is given by our function right here. And we want to find the average velocity over the given time intervals and predict the instantaneous velocity after 30 seconds. So what we're doing here is it's like we're looking between 30 seconds and 31 seconds, and then we're closing that gap. 30 to 30.5, 30 to 30.1. So you can see how those increments are getting shorter and shorter. And what we can do is start to see a trend of as those get shorter and shorter, we can pretty much assume or at least estimate what's happening instantaneously at t equals 30. So setting this up, what we're doing is really we're evaluating, oh, that's what I want to mention too. Sorry, average velocity. So with our calculations here, we're going to be kind of talking about the change in distance over the change in time. And this is going to relate to our average rate of change. So when we calculate this, our average rate of change, it's like we'll take the output of the second time from h minus the output from the first time over the difference in the times provided. So what we're seeing here is change in distance over change in time. And if you think of things that are distance per time, in this case, it's meters per second, feet per second, miles per hour, those are things that create velocity. So where it's using the term velocity, we can relate that to our average rate of change with this change in distance over change in time. Okay, so this is the setup. What we can do is we can see we're keeping our first time at 30, but what we're doing is we're changing the second time. So really for average rate of change, what we're taking is what's the output for the second time, and then subtract away h of 30, and then take that second time minus 30. And what I want to do here is show you how you can set this up in Desmos for some kind of quicker calculations. I mean, you can set this up in your calculator and definitely plug away, but Desmos has some nice features that can make this even easier. So what we can do is we can set up our function. It definitely likes to use x as our input, so we could keep it as h of, and I would just use x for the input value, and then we'll go 80 plus 48x minus 0.5x squared. So there's my function. Off to the right, it's creating a nice little graph for me. But then what I can do in this next step is have it set up my calculations. We could even use a table for this, but we don't need to go that far with it. So what I'm going to do is, for the first one, it would be h of, and then t2, which in this case is 31, subtract away h of 30, minus, and then we're going to do 31 minus 30. So we're getting a 17.5. Then for the next one, what I'm going to do, what's nice about Desmos, is I can just edit where I have 31. I'm going to replace that with a 30.5. And then just make sure you replace it in both spots, and that'll be a 17.75. And then the next one, we're going to change it to a 30.1. So make my edits in both spots, 17.95. And then for the last one, making it a 0.1 after the decimal for 17.995. So what we can do with this is start to see the trend that it's getting closer and closer to 18. So as we get infinitely close to 30, we can at least predict that that velocity after 30 seconds is likely 18. So to make a sentence, we could say after 30 seconds, let's go with we expect, just to put in some wording that we're making a prediction here. We expect the instantaneous velocity of the rock to be 18, and then our units would be meters per second. Did I make English there? After 30 seconds, we expect the instantaneous velocity of the rock to be 18 meters per second. Awesome. Sometimes I get lost in plugging in the numbers. Need to make sure it also makes sense in the sentence. So with this one, it was all average velocities as we used our formula for average rate of change. But with that, we can get an idea of what we expect for the instantaneous velocity as we make those intervals smaller and smaller. Okay. Next up is an example where it's more about the visual of instantaneous velocity and making estimates in that form. So with this one, we have a ball being thrown, we have feet, seconds, times along the x-axis, heights along the y-axis, and we have our function 64 minus 16 times t minus 1 squared. Okay, so our first question is describe the behavior of the ball on the time interval 0 to 1, and then from 1 to 3, and then what do we think is happening at t equals 1. So 0 to 1, that's where we're on this part of the graph. So what we can see is the ball's going upward there. So as time is passing, it's going up. We're getting a higher height, a taller height rather. So with that interval, I'll just make a note that we expect the ball is going upward. It's increasing in height. And then from 1 to 3, the ball's going downward and basically until it hits the ground. All right, and then what we want to know is what is happening at the instant t equals 1. So with that, imagining what's happening at this exact point with the ball. So those intervals, that was kind of describing an average rate of change, an average of increasing, an average of decreasing. But now with this, we're talking about just one moment in time. What's that ball doing? So at that point, it's up in the air and it's at its maximum. And technically, it's not moving. It's not going up, it's not going down. It is just stalled for 1 second as it switches from increasing to decreasing. So here it's at its peak, and it's technically not moving at that instant. So those are just some estimates that we're making looking at that graph, but a difference of this kind of average change that's occurring versus an instantaneous change where we're evaluating what's that ball doing at a single moment in time. So let's say we want to estimate the instantaneous velocity at the point t equals 0.5. So t equals 0.5, that's when the ball is right here. And with this, we just want to draw, and we basically want to find the slope of the tangent line. So what we're doing for this, and we're just going to sketch this and estimate as best we can, but I do really think about zooming in as much as possible, and then we're just trying to match our slope here. Trying to match the slope of the line, something like this. So it's kind of weird on my screen like this, but what we could do is if we had this printed on paper, you could take a ruler and you kind of just set up that ruler so it scooches against that line just where it's touching, and you try to match up that rate of change as best you can. So let's go ahead and continue this on something like this. And at this point, we are truly just estimating as best we can. So we're just getting an estimate, something that's close here. So that's what I'm thinking my tangent line roughly looks like. And really all I need is I have my one coordinate here. I have my second coordinate now here. I just wanted a clear second point so that I can map this slope. So down here we have a distance of 0.5. And then here, I believe our units are 4s, so this would be 8. And then technically we're going, down 8, left 0.5, so it'd be down -8, left -0.5. So for my slope, rise over run, I'd have -8 over -0.5, which is going to be a positive 16. So if I wanted to make a nice pretty sentence for this, I'd say the ball is going upward at 16 feet per second after 0.5 seconds. So in that instant of 0.5 seconds has passed, the ball has a velocity of 16 feet per second. Okay, same idea, but +1. This one's actually a bit nicer because when we're here, what should happen is when we draw this line, and again, what we're drawing here is the tangent line. So we're trying to match up the slope just at this point. When we're at these maximum or minimum values, it's going to create a horizontal tangent line. That's what we're seeing here, which is a line with a slope of 0. So this right here, you could get another coordinate and think of rise over run again, but what it's going to give you is a big slope of 0, which just confirms the ball is not moving after 1 second. Okay, last one here at t equals 2. Right here. And then let's just try to match up this slope as best we can. And not super great with the screen, but we'll just do the best we can. Yeah, sure. Something like that to second coordinate. So let's see, that is down 16. And then to the right by 0.5. So for slope, we'll have a rise of -16, run of 0.5, so -32. So with this one, because it's negative, that means the ball's going downward. Downward at 32 feet per second after 2 seconds. So with this, we get these different velocities, these different rates of change at these different moments in times. So each one's just this instant of looking at one coordinate, but it's this kind of idea of trying to match up the slope at that exact point. And we just need a second coordinate so that we can figure out what that slope is doing.